These are the notes for section 5.5. This section covers systems of inequalities. So here we want to talk about solving a system of inequalities. Now before we get to a system, we want to just take a look at solving a linear inequality in two variables, and then we'll also talk about solving a linear inequality that only has one variable. If you think about solving inequalities, most of the time we have a number of solutions, and so we write our solution in terms of a set or maybe an interval notation, those kinds of things. When we're solving an inequality with two variables, we're looking at a set also, but we're looking at a set of ordered pairs. So it might be a set that has, again, a number of ordered pairs. Okay, there might be, a whole region that we would have to list. Now, obviously, that's going to be very difficult if we have an infinite number of ordered pairs in our solution set. And so instead of listing them all out, what we do is we graph and show our solution set by shading the solution region. So these graphs are all going to be done on a coordinate plane, and we're going to look at what would the solution be and then shade that solution region. Well, let's take a look at an inequality here, x plus y is greater than 4. So here we're looking at the points where the sum of the x and y is greater than 4. Well, what I've done is I've gone ahead and graphed all of the points in which the sum of x and y is equal to 4. So I've graphed the equation of this line here, y equals 4 minus x. That's this line. Now, what that line does is it splits my coordinate plane into two parts. I call them half planes. There's one part below and there's one part above. And I'll say that the solution set to my inequality is going to be one side of this plane or the other. So which one is it? Are these points up here going to satisfy my inequality, or will these points down here satisfy my inequality? Well, one easy way to tell is to pick a point and check. 0, 0 is the easiest point to check. We'll always use 0, 0 unless 0, 0 happens to be on our boundary line here that splits our graph into two parts. If I check 0 and 0, does the sum of 0 and 0 create a number bigger than 4? No, that's false. So that kind of tells you that this region down here does not contain my solutions. I could check any point in this region, in fact, and I would find that it would not satisfy my inequality. Take this point here, negative 1, 3. If I put negative 1 for x and 3 for y, again, that does not satisfy my inequality. Maybe you think if I make my number large enough, it might work. Well, there's the point negative 5, 5. Again, if I add those together, I still have a sum that's less than 0, so that doesn't work either. If I were, on the other hand, to pick a point on the right side, say the point 3, 3, and substitute in 3, 3 does satisfy my inequality, so that is on the correct side. So the solution set for my inequality would be all of these points on the right side of my boundary line. We call that a boundary line that splits our coordinate plane in half. Well, what about the points that are actually on the boundary line? Say the point 2, 2 right here. Does that point satisfy my inequality? If I substitute 2, 2 into here, I have 2 plus 2 is greater than 4. Is that a true statement or not? Well, no, that is not a true statement. 4 is not greater than 4. That's a false statement. So that point and all of the other points that are on this boundary line are also not a part of the solution. To show that, we draw this boundary line as a dotted line. So I'm going to do this in red. Dotted line here. The dotted line means we're not including any of the points on the line, but then we certainly would shade this region to the right, which says any points immediately to the right would satisfy this line. Now, some of you might wonder if there's any generalizations we can make for which sides to shade. Here's the generalization that I'll tell you. If we were to take this inequality and solve for y, subtract x on both sides, we would have y greater than negative x plus 4. Now, do remember when solving, if you divide or multiply by a negative number, you'll have to reverse the inequality symbol. Once we have y by itself isolated, we can use this generalization. If we have y greater than, or obviously y greater than or equal to, we will shade to the right or above, right and above. I shouldn't say right, I would say above. Shade above. Shade above the line. So this is kind of the above part of my line. It's kind of a little bit hard to describe because our lines are diagonal, but I think you'll understand shade above. If we have y less than, or y less than or equal to, then we want to shade below. Well, since I brought up the greater than or equal to and the less than or equal to, what difference does that make? Well, if I had, in this case, x plus y is greater than or equal to 4, you'll now say that that point that we suggested, 2 plus 2, greater than or equal to 4, now does satisfy my inequality. So if I were to have greater than or equal to, I would include all of the points on this line, and then I would show that by making this line a solid line. So if we want to include the points on our boundary line, we make it solid. If we don't want to include the boundary points, the points on the boundary line, then we make it dotted. Let's take a look at a couple of examples here. Let's say I'm graphing 4x minus 2y is greater than or equal to 8. 4x minus 2y is greater than or equal to 8. So the first thing that I need to do is I need to graph my boundary line. Now there's a couple of different ways to graph the boundary line. You could pick out the x-intercept and the y-intercept and plot those points and then draw the line that crosses those points. To find the y-intercept, we substitute 0 for x. To find the x-intercept, we substitute 0 for y. Simply done. If I substitute 0 here, I would have y equals negative 4. If I substitute 0 for y, I would have x equals 2. We can plot those 2 points, 2, 0, 0, negative 4, and we can draw our graph in. I would prefer to get more points, and so I'm going to actually isolate the y. So subtract 4x from both sides. 2y is greater than or equal to negative 4x plus 8. And then divide on both sides by negative 2. Now dividing by negative 2 will again reverse the inequality symbol, and then obviously it'll change the signs here. Now I know that my equation has a y-intercept of negative 4, which on my graph is 0, negative 4, and it has a slope of 2, which is 2 over 1. So now I can get many points on my graph and make sure that I have a good representation of where my line is. My slope goes either up 2, right 1, or down 2, left 1. The next question that I have to answer is, do I want to draw this line in as a solid line or as a dotted line? And here we'll look at the inequality. Does the inequality include the points that are on the line or not? In this case, we would say yes, it does include. So we're going to draw our line in here as a solid line. Solid line. The next thing we need to decide, and this is the last thing, is which side of the graph to shade on. Do I shade above the line or do I shade below the line? We looked at 2 different ways to tell this. If you have this solved for y like I did, then you can simply look at the inequality. Y less than or equal to says shade below. So we would shade below. The other way to do it is to pick a test point. If I pick the test point 0, 0, we can substitute it into our original equation, and then we can check to see if that's correct or not. So here we'd have 0 minus 0 greater than or equal to 8. Is that a true statement or a false statement? Well, that's a false statement, so we would not shade the side with 0, 0. Instead, again, we would shade this other side. So there's the solution to my linear inequality 4x minus 2y is greater than or equal to 8. One other thing to talk about here is what happens if we have an equation that just has one variable. I thought that might have been above here in my notes, but it doesn't look like it is. So we're going to talk about that next. What happens if I have an equation that just says y is greater than or equal to 2, and we're graphing this on a coordinate plane? Well, y greater than or equal to 2, I'm going to start by graphing the boundary line. The boundary line here, since I have just y, that boundary line is a horizontal line right here at 2. Now, I have y greater than or equal to 2, so would I shade above or below? Well, certainly greater than or equal to would be above. Another example with x would say x is less than negative 1. X is less than negative 1. Well, since we have only x this time, we are going to draw our boundary line as a vertical line. Now, this inequality does not have the equal attached to it, so this time we will make that a dotted line at negative 1. X less than would be to the left side of negative 1, so we would shade that in over there on the left side. The next thing we want to look at is solving a system of inequalities. A system just means we're going to have a group of them, and our solution set would be the ordered pairs that fit all of the equations, or inequalities in this case, that are in the system. So here what we're going to do is we're going to sketch the graph of each one of our inequalities. So you see that I've done that here just for a random example. I've got an equation, a boundary line drawn in here in green, one in blue, and one in red. What I've done is I've drawn the arrows in of where the shading would be. And what I want to do now to finish this problem off is to darken in where my triple shading is. That would be the points that satisfy all three of the inequalities. So I darken that region in, and every point in that region should now satisfy all three of my inequalities, and that's what I'm looking for. So let's look at an example of that. Here our system is x minus 3y is less than 6, and 2x plus 3y is greater than or equal to negative 6. So let's start with this first inequality, x minus 3y is less than 6. As I said earlier, what I suggest is that you solve for solve for y so that we can graph this using a y-intercept and a slope. I'm going to have to divide by negative 3. When I divide by negative 3, I have to reverse the inequality symbol. So y greater than, here I have positive 1/3 x, and here I have minus 2. So y-intercept starts at negative 2. The slope will go up 1 and right 3, up 1 and right 3, or down 1 and left 3. And we want to draw this line pretty much all the way out because we're not sure where it might cross with the other line. This one is less than and not less than or equal to, so we're going to sketch it in as a dotted or dashed line. What about the shading? Well, we can do the test point, or we can see that y is greater than, so that tells us to shade above this line here. Alright, for the next equation, 2x plus 3y is greater than or equal to negative 6. Let's subtract 2x on both sides, and then divide on both sides by 3. That gives me negative 2/3 x minus 2. Notice I did not reverse the inequality here because we're dividing by a positive number. This has a y-intercept also at negative 2. This time my slope is 2/3, so down 2 and right 3, or up 2 and left 3. Now, here I have a greater than or equal to, so I'm actually going to make this a solid line down through my points. And here I'm going to look at the inequality greater than or equal to say shade above. So now I have both inequalities in my system graphed. I'm looking at where I have the double shading. And I want to darken this in or somehow show that this is my final answer. This region in here is where I have the double shading. Every point or ordered pair in this region here would satisfy both of those inequalities.